So now we're in section 3.6, rational functions. And I'll be honest, rational functions, it's going to be kind of a chunky section just because there's different types and things we need to think about. And hopefully at the end, however, you'll have a really good idea of what a rational function looks like. So rational functions can be written in this form: p of x over q of x, where p of x and q of x are polynomials. So understand that a rational function is not a polynomial, but it is made by the division of two polynomials. So for example, we have this rational function right here. F of x equals x squared minus 3x plus 2 divided by x squared minus 9. So this is a polynomial function in the numerator, polynomial function in the denominator. That creates the rational function. When we think about the domains of rational functions, you should think about the fact that rational functions themselves, because they're made up of polynomials, but you have division, mean that we have one thing that we really need to pay attention to, and that is the fact that in a rational function, the denominator cannot be 0. So we cannot divide by 0. So when we see a rational function, we should think, okay, what would make the denominator 0? Because that's going to be an issue for my domain. So when we think about this one, we see that the denominator here is x squared minus 9, that cannot be equal to 0. We can factor that pretty easily. It's the difference of squares. Cannot be equal to 0. And that tells us that x cannot be equal to negative 3, x cannot be equal to 3. So of course in set notation, trying to get a little more mathy here, all x such that x cannot be equal to negative 3, positive 3. That would be the domain. What it means is we could pick anything else. Any other number that you can plug in there is going to be fine, honestly. The only issue that we're going to have is, of course, with that 3 or negative 3, because we cannot divide by 0 and they make the denominator 0. So now let's, take a look at this. Graphing rational functions. There are pieces to this that we want to think about. There's some common things when we did polynomials, and then a couple new things because we have rational functions. So we can still think about the intercepts of a rational function. In terms of the y-intercept, that is still just what happens when x equals 0. So you can plug that in. You can see that your numerator is going to be 2. If you plug in 0, your denominator is going to be negative 9. So we can pretty easily find a point on the graph of a rational function, which is 0, negative 2 ninths. So that's a value that we could put on our graph. For the x-intercepts, it is the same idea. You let the function be equal to 0 or let y equal 0 and find out the values that make that true. What we really want to remember here is that when you have a fraction equaling 0, the only time a fraction can equal 0 is when the numerator equals 0. So we take the numerator, we set it equal to 0. If a numerator is 0 and denominator is anything else, 0 divided by anything else besides 0, is going to give you 0. And that's an okay number. That's a real number. So we look to see if we can come up with anything there. We have x and x minus 1 and 2. So we get x cannot be equal, I don't need to do that. Sorry, I'm thinking my domain here. So that gives us x equals 1, x equals 2, and more importantly, it gives us the point 1, 0, 2, 0 as our x-intercepts. So now we have a lot of values here. And so now we can think about a sign chart. And that sign chart is very similar to when we did polynomials. We want to think about what happens when this function gets very large negatively, what happens when it gets very large positively. We want to think about any x-intercepts, and we also want to think about any issues with the domain. So you want to think about the fact that because we cannot have negative 3 or 3, that those values are going to cause an issue, and they are a place possibly where the signs could change. So I'm going to put negative 3 and 3. And I'm going to I'll put my y-intercept. That's technically not necessary, but it will allow us to put the point on. When I put 3 or negative 3, I'm going to put this line here. And that's going to tell me, hey, this is not a point. This is just a place on my graph of my x, my rational function, that is going to be an issue. Let me come over here really quick and talk a little bit about asymptotes. So an asymptote is a line that a graph gets closer and closer to as it goes farther and farther away from the origin. Okay, so like this. There are 3 types of asymptotes: horizontal, vertical, and oblique. So I'm going to focus right now on horizontal and vertical, and I'll start with vertical. So vertical asymptotes are places in a graph where a vertical asymptote is a straight line up and down. It's like this. But it is like this invisible line that your graph will never touch. And you'll see why with these rational functions. So notice the graph of a rational function has a vertical asymptote at x equals r. So that's a line, that's a vertical line, x equals r, if r is a real root of x, but not p of x. So what that means is it makes your denominator 0, but not your numerator 0. Makes your denominator 0, but not your numerator 0. We did that right here. We found out from the domain of this, which is the first step that we did, that we could not have 3 or negative 3. Those are values that make the denominator 0. That tells us, if you go to your page and you see vertical asymptotes, that tells us that x equals negative 3, x equals 3 are going to be vertical asymptotes on our graph. So what that looks like, what I'm going to do just to remind myself is when I have a vertical asymptote, I can just draw, notice this is x equals 3. So it's just every value where x is 3. So I'm just going to do a line like that. I'm also going to do one at negative 3. And what I know is that my graph will never touch that. Because if we were to put in 3 or negative 3, we end up dividing by 0. We get some number over 0. And that is, you cannot divide by 0. So our graph will never touch those 2 lines, 3 or negative 3. These 2 lines are not part of my graph. They're just going to help me shape my graph by knowing that my graph cannot touch those values. Now, horizontal asymptotes are a little more, a little more. And you actually do talk about these in calculus as well. So notice we have a rational function. It's got, this is a lot of notation just to remind you that that's a polynomial divided by a polynomial. That's all you have to think about. Okay. Depending on your situation, so notice you could have this situation, this situation, this situation, or this situation, and we'll be looking at those today. And it all has to do with the degree of your numerator and the degree of the denominator. Now, in our first example, let's come back over here. Our first example here, they are the same. So the degree of the numerator is the same as the degree of the denominator. So that's going to be situation 2. So we're talking about horizontal asymptotes. The idea here is what is happening as x gets really, really big positively or really, really big negatively. We've talked about this in terms of polynomials, but in terms of rational functions, you have a fraction there with your rational function. And so by choosing numbers for x, you're going to find that as x gets really big, there's a few different things that can happen. As x gets large negatively, there's a few different things that can happen. So we have this situation where the degrees are the same. So that's telling us that we're going to have an asymptote at the line y equals a sub n over b sub n. All this is, notice all this is the ratio of the coefficients of the leading term. That's all it is. This is because this function is basically getting very large at exactly the same rate. When we're talking about values where an x is really large, we don't even care about these. The rest of the terms don't matter when you're just conceptually thinking about x getting very, very large, positively or negatively. The only thing that matters is that you're going to be doing some version of x squared over x squared. And again, please, put in 1,000 into your numerator and put 1,000 into your denominator and try it out, and you will see that the ratio of those things are very close to 1, because x squared divided by x squared is 1. So I'm going to erase that because I don't want it there, because we do have a complete function here. I'm just getting you to think about what's happening when this x gets very big. So what we're saying here is, as x goes to infinity, y is going to be heading towards 1, positive 1. As x gets large negatively, as we go this direction, y is going to be getting very close to 1. So what's happening to our function as we head away from the origin is that our function is going to get very close to 1. It might come up from the bottom, it might come up from the top, come down from the top. That's what we have to find out. So we have y equals 1 as our horizontal asymptote. That is, not surprisingly, a horizontal line. So here is our horizontal line. Okay, so hopefully you can kind of see my colors there. Whew, that's a lot of work. Okay, and again, this is because degree n equals 2, m equals 2, so n equals m. So we're just looking at the coefficients of the leading terms. So we have an x squared over an x squared. That's just 1 over 1, which is 1. We'll see more examples of this for sure. So now I think we're ready for our signs. Here. So we already know that this is what's going to happen as we get close to negative infinity or infinity. Very different than polynomials, having us approach a number. And then we're still doing the same idea. We're just going to put in values and see, do we get something positive or negative? We're going to look within these numbers at our signs. So I am going to write this in its factored form, just because I feel like that's going to be easier for me, because all I care about is positive or negative. So I can just think about, do I have positive or negative value coming out of this interval? And then that will help me determine whether I'm above or below the x-axis. Okay. So we can test something between -3, negative infinity. So let's say -10, my fave. So we put in -10. I'm plugging it in just to see, am I getting something that is positive or am I getting something that is negative? So I put in -10. Notice I'm going to have -12 times -11 divided by -13 times -7. So I'm going to have negative times a negative divided by a negative times a negative. So that's a positive divided by a positive, so that's positive. So that's telling me that my function, this rational function, is going to have positive values, meaning above the x-axis, all the way from negative infinity to -3. Now, what that looks like on the graph, it's a really big deal that we have to get close to our asymptotes. So this function, don't write this, it's not going to do something like this. It's just not. It has to get close to the asymptotes that we have found. So it's telling me that I need to get close here and I need to get close here. This must be what my function does. By definition of an asymptote, I need to be approaching these asymptotes. That's what it has to look like. I'm also going to put in my little point here, 0, -2/3. So I'll put in my y-intercept value that I have. We also have those two x-intercepts as well that we can put in. That's over here, 1, 0, and 2, 0. There we go. Okay. And moving on. All right, so between -3 and 0, so remember this is -2/9 here, I could test, say, -1, something in between there. I plug it in, take a look at our factored form here. If I put in -1, I'm going to have negative, 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 positive. Okay, so negative, negative in the numerator, negative in the denominator times a positive. So that's going to be a positive divided by a negative, which is a negative. So that tells me that I'm going to be negative all the way up to 0. But again, I've got to get close to that asymptote there. So I've got to be close to the asymptote, but I've also got to get to that y-intercept. I can't go above the axis because I don't have another x-intercept. It's not possible. Okay, so I'm just right there. All right, now let's go back here. I pick a value between 0 and 1. I'm going to pick a half. All I care about is the signs. I'm going to have, if I put it into my original function in its factored form, I'm going to have negative, 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 positive. So again, that's 3 negatives and a positive, that's negative. So I'm going to stay negative. It's not surprising because I actually need to hit this x-intercept right here. So I need to stay below the axis. So that's actually not something I have to worry too much about. Between 1 and 2, let's pick 1.5. And when we put that in, let's see if anything exciting happens. I'll do another round of just showing you the 4 pieces that I'm putting in. So when I put in 3 halves, it looks like I'll have a negative, because 3 halves minus 2, and then I have 3 halves minus 1, so that's positive. Then I have 3 halves minus 3, that's negative, and then I have 3 halves plus 3, that's positive. So it looks like I'll have a negative divided by a negative, which is positive. So from 1 to 2, I'm going to be positive. I'm going to be above the x-axis. But of course, I have to get to that other intercept. So I must be having to do, I'm doing something like this. I know I'm kind of doing this in pieces, so it's not quite as smooth as it could be. Maybe I'll fix that for you. All right. Now I'm going to pick something between 2 and 3. So again, I guess 2.5. You know, if you want to do a decimal, that's fine, 2.5. Putting that into the numerator, it's going to be positive, positive, divided by negative, positive. So that's going to be negative. So now I'm going to head back down. Now I'm going to be negative values, but I also have that other vertical asymptote I have to touch. So I'm going to head down by choosing that. You know, I'm going to go down, like choose to get close to that, like that. So it's just going to get closer and closer. It's literally going to get infinitely close to that line. It's never going to touch it. Never going to touch it, get infinitely close. And then you might be able to guess what our last piece looks like. I'm not sure. But understand we have no more x-intercepts that we can deal with. There's no other times that we can cross the x-axis. And we just pick something between 3 and infinity. I'm going to pick 10. And when I do that, notice my numerator, positive, 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 positive. So, not surprisingly, I will have positive values. Now you might think, well, what is this supposed to look like? All we know is that they're positive values, but we also know they have to hug the vertical asymptote. They got to get infinitely close to these 2 asymptotes. So I'm going to show that by getting close to the asymptotes with my positive values. And now we have a picture of what this rational function looks like. It's just a sketch, but as you can see, it actually has quite a few values on it that make it so that it's a pretty, good representation of what this function looks like. So these are all kind of the pieces that we need to think about with our rational functions. So we can think about what's the issue, any issues with the domain, x-intercepts, y-intercepts. We can think about asymptotes, and then we can make a sign chart and just go from there. So it's a lot of pieces, but it does give us a good idea of what this looks like. Now I'll do the next one here. This is one of your most basic rational functions, 1 over x. And I want you to notice that it has both a horizontal and a vertical asymptote. We can plug in some values if you want to see what it looks like here, if you want, you can pause and put in these values and, you know, see what you get. We cannot plug in 0. Okay. So notice we cannot plug in 0 because it makes the denominator 0. We're going to have a vertical asymptote at x equals 0. Otherwise, we have some pretty standard values here that come from just plugging that into 1 over x. I'm going to see if if a different color works better here. So we have a vertical asymptote at x equals 0. And then I want you to think about the fact of what would happen if x got very large positively or if x got very large negatively. So when you think about this, when x gets very large positively, 1 over a really large positive number, so as x goes to infinity, you know, out here over on the right side of our graph, you should think the fact that y equaling 1 over something really large is something very, very small. So, I mean, you can just picture if I put x equals 1,000, if I put x equals 1,000,000, that number is going to be teeny tiny. So what's happening as x goes to infinity is that y is going to 0. And as x goes to negative infinity, the same thing's happening. 1 over negative 1,000, 1 over negative 1,000,000 is still very, 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 very tiny. So y is going to 0 as well. So that tells us that our horizontal asymptote is y equals 0. And so we can put that on here. We don't really need much more, to be honest. We have some points that we found, and we have, you know, no x-intercepts, and we have no y-intercepts. Our domain is just that x can't be 0, and we can see that because it's the vertical asymptote. So what I want you to see here is, I mean, again, it's pretty basic. What you're seeing, like at -2, you have -1/2. -1 is -1. -1/2 is -2. And it makes sense because we have these two asymptotes that we have to get close to. So what's going to happen is it's going to look like this. And then on the other side, we have something very, very similar, but in the positive direction. So, you know, you have something that looks like this, and you've got to just get close to those asymptotes. Again, you got to be close, close, close. I don't love that, so I'm just gonna, it looks pretty good, but I'm just gonna make it a little bit better here. You're just gonna get close to both asymptotes, and that's all that 1 over x is. That's, again, one of the most basic rational functions. In terms of this horizontal asymptote, if I come back to this example here, notice in our case here, now I gotta come back here. So when we think about the horizontal asymptote, the numerator has degree 0 because there's no variable there. So it actually has degree 0. The denominator has degree 1 because you just have x to the 1. So what we see is that n is less than m. So we come back here and we see, oh, okay, well, if n is less than m, if the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is the horizontal asymptote. And that's what we found, kind of sussing it out in another way. But that's the idea. That's what's happening there, is that your numerator is not getting big like your denominator. So as x gets very large positively or negatively, the y values become very, very small, approaching 0.